Hello gems, welcome back to another video. In this video, we'll be discussing the previous year BITSAT questions from the chapter of Nuclei. Now, the grant for BITSAT 2022 is on. Make sure you check out all the BITSAT content that is already available on this channel. And without even wasting a fraction of second more, let's begin with this video. So question 1, 2, 3 from the super easy category, let's give it a try. Okay, so question 1, boron rods are used in nuclear reactor 2. Okay, so basically in nuclear reactor, you have nuclear fission happening, and at the end of every fission, you'll have some neutrons which are released, right? Now, these neutrons which are released will again collide with your parent atom or your fuel atom, example uranium, and they will again undergo fission and again release a lot of neutrons, right? So this is a kind of a chain reaction, right? So an atom undergoing fission releases neutrons again hits your or collides with your parent atom and again generates a lot of neutrons, right? So this chain reaction should be controlled, and that is why we use this boron rods. And how will this boron rods control this chain reaction? So they basically control it by absorbing the excess neutrons which are there. Okay, so they'll absorb the excess neutrons, thereby causing less fissions and thereby controlling your reaction, and which might otherwise lead to an explosion if not controlled. Okay, so they play an important role in absorbing the excess neutrons which are there and thereby controlling the chain reaction. Okay, now let's come to question number 2. Uranium decays into thorium and helium. So this is an radioactive atom which decays into two atoms. Now this is a heavier atom, as you can see, and this is a lighter one, right? So you are supposed to comment about their momentum and kinetic energies. Okay, so if you think suppose this uranium began at rest, so initial momentum will be 0, of course, right? And this decays, right? So the force was completely internal, there was no external force, right? So the momentum should be conserved, right? So initial momentum was 0 in this case, right? And final momentum will be also 0 because momentum is conserved, and this decays due to internal forces. There is no external force in this process, right? So final momentum should be also 0. So the momentum of thorium should be plus the momentum of your helium should be equal to 0, right? These are the two final products, right? So momentum of this plus momentum of that should be equal to 0. So this implies that the momentum of thorium is equal to momentum of helium. Basically, they are numerically equal but opposite in directions. Okay, so yeah, you can see it from here. So momentum, these relations are wrong. They are momentum, in fact, of thorium and helium are equal numerically. They are just moving in opposite directions. Okay, now what can you say about the kinetic energy? Kinetic energy, you can write it in terms of momentum, which is p square by 2m, right? So basically you can see that kinetic energy here, momentum is constant, right? Both of them have the same momentum of thorium and helium is same, so p is same for both. You can directly say that your kinetic energy is inversely proportional to mass. Okay, so the heavier the atom, the lesser the kinetic energy. Okay, so the heavier the atom, the lesser the kinetic energy. Actually, you can think about it, the heavier the atom, the slow it will move, right? Due to momentum conservation also, the heavier it is, the slower it will move. And since kinetic energy is half mv square, v is less, so the heavier atom should have less kinetic energy. Okay, so basically your thorium will have less kinetic energy, so kinetic energy of thorium is less than the kinetic energy of helium. Okay, helium is light, so that's why it will move faster. Okay, so and will have higher kinetic energy. Now let's come to question number 3. Half-life of A. So you have two radioactive substances over here, A and B. So half-life of A is 1 hour, half-life of B is 2 hours. Okay, I hope you know what that means. Okay, so here are some comments about them, and you are supposed to select the comment which is correct. Okay, so A decays slower. So if you see A decays slower, so suppose we begin with an initial concentration of N0. Okay, now if you see after 1 hour, the concentration of A will become N0 by 2, right? That is what is meant by half-life, right? After this time, the concentration becomes half of the initial, right? So after 1 hour, it will become N0 by 2. but for B it will take 2 hours to become half. Okay, so for the same concentration N0 to become half, for B it will take 2 hours. Okay, 1 extra hour. So basically A is decaying faster, right? It's not decaying slower, it's decaying faster. It gets to half of its concentration in 1 hour faster than B, of course, right? So this is wrong. Now you are told about their decay constant. Now if you see half-life and decay constant are inversely proportional, right? If you see T half is 0.693 basically that is log to the base E2, and divided by lambda. So if you see T half is inversely proportional to your lambda, right? So if you see the one which has higher half-life will have lower decay constant. So higher half-life, lower decay constant. Okay, so B will have lower decay constant. Okay, so it will be somewhat like this. Okay, so as you can see here, A should be greater, right? Decay constant of A is greater. Here it shows that decay constant of A is less than B, which is again incorrect. Okay. Now let's come to C. C says that the reactivity, basically the rate of A is greater than rate of B. If both of them begins at the initial concentration in both of them is N0. Okay. Now this is true because you can see over here A decays faster, right? So the rate of reaction for A is faster. Basically R, if you see, is lambda times of N, lambda times of N0, right? Where N0 is the initial concentration, right? So initial concentration is same for both. R is directly proportional to lambda, right? So RA will be greater than RB, same relation. Okay, RA will be greater than RB. So option C is the correct choice over here. Mean life of B is less than A. Of course not, because mean life and half-life are directly proportional. Okay, you can see that T half or your mean life is 0. T half is 0.693 times your mean life. Okay, basically your half-life and mean life are directly proportional. So higher half-life means higher uh, mean life. Okay, so mean life of B should be more, not less. Okay, so again D is also incorrect. Only correct option is option C. So that was from the super easy category. We have few more questions from the super easy category to deal with, and then we'll move to the easy category. So question 4 and 5 over here, we are still there in the super easy category. Question 4, from 2009, nuclear energy is released in nuclear fission since binding energy per nucleon is, okay, is it larger on the parent side, larger on the fragment size, depends, or same on the both side. Now if you see a basic nuclear reaction, we'll just write it this way: X decays into Y plus Z. Okay, so you are supposed to tell where is the binding energy per nucleon greater. Okay, now X decayed because it was unstable, right? It was radioactive and it was, we can say that it was unstable, whereas Y and Z are comparatively stable, right? Now remember one thing from today's discussion, that whenever an atom is stable, it means that it has higher binding energy per nucleon. Okay, the binding energy per nucleon is higher for those which are stable. Okay, so stable implies that binding energy per nucleon for that particular atom is greater. Okay, so this is, if you see, this is the fragment side, right? This is the parent, it breaks into daughter nucleus, right? So of course this is stable, so this is the fragment side. These are the two fragments, so the binding energy per nucleon is greater on the side which is stable, which is the fragment side. Okay, so it's larger on the fragment side. Okay, so please remember that whenever an atom is stable, its binding energy per nucleon is high. Okay, now let's come to question number 5. Here you are given the atomic mass numbers of two elements A and B. Okay, you are supposed to comment about their radius and binding energy per nucleon. Okay, so these are the binding energy per nucleon and these are the radius. Okay, you are supposed to tell which comment about them is the correct one. Okay, now you should know the stability curve for this. The stability curve, in that there is one special thing, that the atoms between 50 to 80 are stable ones. right? So if you see the atom A over here, okay, these are the atomic mass numbers, okay? So the atoms which have mass number in between this are the ones which are more stable, okay? And if you see our atom A is in this range, right? It is between 50 to 80, it's 64, so it will be stable, right? And just now I told you that any atom which is stable should have higher binding energy per nucleon, okay? So it will have higher binding energy per nucleon. So atom A will have higher binding energy. Where is that? So either it's option A, no, it's not option A. Here B has a higher energy, right? So it's not option A. Okay, we can cancel that out. It's not option C. So either it's option B or option D. Okay. Now let's go for the radius. Radius we can actually compute using the relation r equals r naught a to the power 1 by 3. Right. This is the relation between radius and your mass number. Right. You can directly see that there is a direct relation like this. Right. So you can take the ratio RA by RB, that will be basically A, the basically the atomic number of A divided by atomic number of B, atomic mass number I mean, raised to 1/3. If you see 64 is 4 to the power 3 and 125 is 5 to the power 3, right? So RA by RB will be basically that power 3 will cancel with that 1/3 and you'll have 4 by 5, okay? Now, if you see very interesting over here, option C, first part is correct, but this is incorrect, okay? So we have to see whether RA is greater or RB is greater. You can easily see that you can write RA into 4 by 5 is equal to RB, right? Sorry, it's RA into 5 by 4 equal to RB, right? So you have to multiply RA with a number greater than 1. Now 5 by 4 is greater than 1, right? It's 1.25. So you have to multiply RA with a number greater than 1 to make it equal to RB. RB is bigger, okay? Again fill it. So you have to multiply RA with a number greater than 1 so that it becomes RB. Okay, so RB is of course bigger, right? So RB is bigger, which is that option B or option D, right? RB is bigger, and of course binding energy per nucleon for your A should be bigger because it's in the stable range, okay? This comes from stability curve, okay? You are supposed to know this thing. Whenever the atomic mass number is in this range, it will be more stable. It's most stable for your ion, okay? We'll come to that. Let's move to the easy category now. I hope these questions were clear. So question 6 and 7 over here, more on binding energy, this time from the easy category, okay? So we'll get to the interesting part in a while, okay? I know binding energy is a kind of annoying, okay? So here you are given the AMU of nitrogen, oxygen, and mass of proton is also given in terms of AMU. You are supposed to tell what is the binding energy for making of this atom, okay? So you can make it from here. The reaction will be basically have nitrogen and then you collide it with a proton and you'll have your oxygen. So basically the binding energy will be the mass defect in this reaction multiplied by c square, right? So binding energy will be delta m, which is the mass defect, okay? Some of the mass will disappear in this reaction, right? The mass on the left hand side is greater than the mass on the right hand side. The mass basically does not disappear, it gets converted into energy, right? So we have a lot of energy over there, right? So that energy is basically mass defect into c square, okay? So that will be same as the binding energy for removing the last proton from your oxygen. So that is what the question is asking, right? Now everything is given in AMU, so you can use this formula. Binding energy is delta M into 931.5 mega electron volts, okay? So this is the formula that you are supposed to know over here. When mass is given in AMU, you can directly use this formula, okay? And if you want the answer in mega electron volts, right? So delta M, the mass defect, times your 931.5, okay? Now delta M, it's easy to calculate. The mass on left hand side minus the mass on right hand side. Okay, so the mass on left hand side, if you see, we have nitrogen and your proton, right? Nitrogen and this is proton, right? So you add the two masses, so mass of nitrogen, I'll write it this way, plus mass of proton minus the mass of oxygen, that will give you the mass defect. Okay, so here you are supposed to calculate it. Okay, you are given the values. Okay, this is something that you will carry forward and tell me the answers. Okay, so once you add this, it will be around something 16 point something something, then subtract this, again it will be 0.00 something. Okay, and that you have to multiply with this, okay, to get the binding energy, and the answer that you are supposed to get over here is 12.13. Okay, so carry out this calculation and see if your answer is coming to option D. Okay, now let's come to question number 7. Binding energy per nucleon for lithium is given as this, and for helium is given as this. Okay, so you are supposed to tell what is this Q. Okay, the value of that Q. This is a question from 2005. Okay, now binding energy per nucleon is given, so let's find binding energy for that particular atom. Okay, so you just have to multiply this, okay, with the number of nucleons. Now what are the number of nucleons? It's basically the sum of protons and neutrons, or basically the mass number, right? So 7 is the number of nucleons over here, and 4 is the number of nucleons for this one. Okay, so for lithium atom, you can easily find out the binding energy for lithium atom will be 7 times this binding energy per nucleon. Okay, this is per nucleon, so we have 7 nucleons in our lithium atom. So the answer is 7 6 are 42, carry 4, 7 5 are 35, 39.2. Okay, and for helium, it's 4 times of this 7.06, 7 6 are 24, and 7 4s are 28, 28.24. Okay, now be careful, in this reaction you can see two helium molecules, right? So basically you have to multiply this answer with 2, so 28.24 into 2. Okay, so basically you will find the difference in these two energies, right? This is on left hand side, that is on right hand side, so difference in their binding energies will give you this heat which is released. Okay, now the special attention that you have to pay over here is that you have two helium atoms, right? So this is for one helium atom, you have to multiply this by 2 for two helium atoms, and then take the difference, and that will give you the energy. Okay, so 24 2, that is 48, and this will be 56. Okay, so this difference you have to find, 56.48 minus 39.2. Okay, so this will be 8, and here you'll have, I think it will be somewhere close to 70. Okay, so this was 48, right? So this will be 2, and this will be 7, right? And this will be 1. So 17.28 or 17.3 approximately. So option D is the correct choice over here. Okay, so basically you have to find the difference in binding energy. Keep this thing in mind. This is binding energy per nucleon. So you multiply it by number of nucleons and see to it that you multiply 2, because here you have 2 helium atoms. This is for 1 helium atom. So multiply it by 2 helium atoms, then the difference, and that is the amount of heat energy that is released. Let's move to some interesting questions now. So question 8 and 9 over here, we have in question 8 a few atoms, okay, with their corresponding binding energies. Here you are supposed to tell which among them is the most stable one. Now you already know that the more stable the atom is, the higher the binding energy. No, the more stable the atom is, the higher the binding energy per nucleon. That is something that you should remember in this lecture. The more stable an atom is, the higher is its binding energy per nucleon. Okay, so here we are supposed to calculate binding energy per nucleon. Okay, and the higher value among this will be our clear winner. That will be the most stable atom, right? So for first one, hydrogen, you can see binding energy is 2.22 divided by number of nucleons, so it is 2, right? Nucleon is nothing but the atomic mass number, right, which is 2 for hydrogen, so it will give us 1.11. Okay, now for helium, 28.3 divided by 4, right? Number of nucleons 4. So 7 point something, okay, 7 point something, not literally, okay. And now for iron it will be your 492 divided by 56. Now it will come to around 8.5, I guess. So yes, let's write that 8.5. And finally we have for uranium 1786 divided by 92, not 92, it is 235, right? Number of nucleons, it is 235, okay. Now if you calculate that, let me check that, it will be around 7.6, okay. So you can see that clearly our winner is iron. Iron has the most binding energy per nucleon and hence will have the highest stability, right? So iron, if you know the stability curve, you could have directly known that iron is the most stable element out there, right? Most stable nucleus out there, okay? So yes, iron, Fe I should write, Fe is the correct choice over here. Okay, let's come to question number 9. Finally, a question from your uh, alpha, beta, gamma decay. Okay, so here you are supposed to tell what is the atomic mass number and Z atomic mass, sorry, atomic mass number and atomic number for your A4. Okay, these are some radioactive reactions happening over there. Okay, so this is the initial value of A and Z. Okay, so this is Z and this is A. Okay, so after one alpha transition, okay, A1 will become, this will be -2, right? -2, and this is -4. A -4 and Z -2. For alpha transition, it becomes A. So if you have an atom like A, Z, I will use X, okay, X, A, Z. So atom like this, if it undergoes alpha decay, then Z will decrease by 2 and A will decrease by 4. Basically, a helium atom is released. So 2, the atomic number will decrease by 2 and the mass number will decrease by 4. Okay, because an alpha particle is released. Okay, so decrease this by 2, decrease this by 4. Okay, now you have beta decay. Since it is not mentioned, the beta decay that you are supposed to undertake is minus. Okay, beta minus is the more common one. So if it's not mentioned, consider beta minus. Okay, now in beta minus, it's opposite, right? In beta minus, what happens is it will become Z plus 1. Okay, this is the case. Okay, atomic number will remain the same. Atomic number will increase by 1. Atomic mass number will remain the same. Okay, so here A2 will become Z plus 1. So 70 plus 1, 71. Mass number remains the same. Okay, now after that again A2 undergoes alpha decay, so decrease this by 2. So A3 is here, you'll have decrease this by 2, 69, and decrease this by 4, right? Alpha decay, decrease the mass number by 4, so decrease that by 4, 172. Now this undergoes gamma decay, so there will be no change. Basically this is an excited state. It will go under transition, nuclear transitions, and there is no change basically in your atomic mass number and your, basically if you have gamma radiations coming, so this is an excited state, it remains the same. Okay, the atomic mass number and your atomic number will remain the same. Okay, they won't change. It is basically gamma radiations are released due to transitions, nuclear transitions. Okay, so finally you'll have the same number 69 and 172. Okay, so A is 172 and Z is 69. So option A is the correct choice over here. Okay, so I hope that was simple. Let's move to some trickier questions now. So question 10 and 11 over here, these are slightly tricky. Okay, you cannot solve them directly by using the formulas and all. So in question 10, you are given a radioactive substance which decays into Y. X is radioactive, it decays into Y. Half-life for this reaction is 2 hours. After time t, the ratio of Nx and Ny becomes 1/4. Okay, you are supposed to guess what is this time t at which this ratio becomes the concentration of X, the number of nuclei of X to number of nuclei of Y becomes 1 is to 4. Okay, so we are given the half-lives. We can see what is the concentration after different half-lives. Okay, so let's do that. Okay, so after 2 hours we can see, after 4 hours we can see, this is the second half-life, this is the third half-life, 6 hours will be the third half-life, 8 hours. So you only have 3 options, okay, 2, 4, 6, or in between them. Okay, so let's see what are the concentration at this different instances. Okay, and let's see if the ratio is 1:4 anytime over here. Okay, so nx, suppose let the initial concentration of x be n0. Okay, y begins at 0, so no issues regarding that. So after 2 hours the half-life is done, so the concentration will fall to half of the original concentration. Now x has decayed half into y. Okay, so this will also become n0 by 2. If you take the ratio, it is 1. Okay, so that is not what we want. Okay, so let's move to our next half-life. Next half-life says the ratio will become n0 by 4, right? So basically your nth half-life, second half-life is 2 to the power n. Nth half-life, the concentration becomes n0 by 2 to the power n, right? So the second half-life, it is 2 to the power 2, which is nothing but n0 by 4. So after second half-life, it becomes half of this, basically n0 by 4. Okay, now if you see the difference over here is n0 by 4, so you have to add n0 by 4 to this. Okay, so basically x has decayed, n0 by 4 amount of x has decayed into y. So this plus n0 by 4, n0 by 2 plus n0 by 4 will give you the concentration over here. Okay, so half plus okay, n0 by 3, n0 by 4, is it? Yes, half plus if I multiply 2 over here, yes. Okay, now again this will become n0 by 8 at 6 hours. If you take this ratio over here, it will give you 3 by 4, right? Or 4 by 3. No, sorry, 1 by 3. Okay, so this ratio is 1 by 3. So again, not equal to this. Let's go to 6 hours. 6 hours, again you divide this by 2. Okay, one half-life has passed. Again the concentration will become half of the initial, half of this. Okay, n0 by 8. Now again n0 by, if you take this difference, it is n0 by 8, right? So n0 by 8 amount of x has converted into y. So n0 by 8 plus this should give you the concentration over here. Okay, so 3 n0 by 4. So multiply this by 2, 6, 6 plus 1, 7, 7 n0 by 8. Okay, so again if you see the ratio over here is 1 by 7, again not equal to this. So the correct choice over here will be between 4 and 6. Actually you can see it. Okay, let me show you. So if you take the ratio over here for 4 hours, 4 hours the ratio is 1 by 4, right? For 6 hours the ratio is 1 by 7. The thing that you want is, sorry, for 4 hours the ratio is 1 by 3. Okay, and for 6 hours it is 1 by 7. The thing that you want is 1 by 4. It is somewhere between these two, right? So yes, that will be this ratio will be when your time is somewhere between 4 and 6 hours. Okay, we are not sure when, but it will be somewhere between 4 and 6, right? Yes, because this fraction itself is between these two numbers. Okay, so yeah, between 4 and 6 is the correct choice over here. I hope the idea was clear to you. Okay, let's come to question number 2. This also will do it by table. So sample A, okay, so you have nuclei A which has half-life of 20 seconds, nuclei B which has half-life of 10 seconds. Okay, these are two different nuclei, okay, undergoing two different reactions. Half-life for first one 20 seconds, second one 10 seconds. Okay, now A1 has initial concentration is 40 grams, and A2 we begin with an initial concentration of 160 grams. Okay, you are supposed to find what is the time t when both of them will have equal number of atoms. Okay, or basically their concentration will be equal. Okay, so that is the time that we are supposed to find. Okay, let's see it through our half-lives. Okay, so if you see, these are different half-lives, right? 20, 40, 60 for different atoms. So what we'll do is we'll plot an interval for every 10 seconds. Okay, so we'll go from 10, 20, 30, 40, 50. Okay, we'll see if we can find in this interval, otherwise we'll have to go till 80. We have option 80 over here. Okay, first we'll see if we can find over here. Okay, so A1 and A2. Okay, so after 10 seconds, what will happen to A1? So its half-life is not yet complete, so we cannot say something about it, right? So its concentration will not become half, it will be greater than half. Okay, so we cannot comment anything about A1 as of now. Okay, but after 20 seconds, okay, one half-life is complete for A1, so its concentration will become 20 grams, right? Half of 40, 20. Okay, after 40 it will become at 40 it will become 10 grams, half of this. Okay, so two half-lives have passed. Okay, if you see for A2, okay, A2 has half-life of 10 seconds. So after 10 seconds, its concentration will become 80 grams, half of this. Again, after 10 seconds, its concentration will become 40 grams. Again, after 10 seconds, 20 grams. Again, after 10 seconds, 10 grams. Oh, nice. We found it, right? Here at 40 seconds, the concentration of A1 and A2 is the same. So option B, 40 seconds is the correct choice over here. Okay, you can actually go on till 60 and 80. At 60 and 80, they will have different concentration. 40 is in fact the only place where they have the same concentration. Okay, so here there will be some concentration, but I'm not sure about it, so I've just left it blank. Okay, so this is the way to do this question. Let's move to the moderate category now. Question 12 over here, the first from the easy to moderate category. You can see that this was the first question that is repeated in 2017 and 2020. Okay, now here in this question you are told that the activity at t is equal to 0 is r0 and the activity reduces to r0 by e when time t equals 5 minutes. Okay, you are supposed to tell what is the time when the activity reduces to half of its initial value. Okay, it's actually very simple. You are just supposed to use this data to find lambda, and from lambda you can actually find this. Okay, let's try it. So basically the equation for activity is r equals r0 e to the power minus lambda t. It's analogous to the radioactivity equation, right? So first here we'll use this data. It becomes r0 by e when your time is 5, right? 5 minutes. Okay, so in place of t we'll put 5, so that becomes 5 lambda. Okay, now r0 and r0 will get cancelled. E to the power minus 1 equals e to the power minus 5 lambda. Okay, I just took that e above. Okay, so that becomes e to the power 1 becomes e to the power minus 1. So minus 1 equals minus 5 lambda, or lambda equals 1 by 5. Okay, unit is per minute. Okay, minute raised to minus 1. Okay, now you have found out lambda. You are just supposed to use it in this now. Okay, so we will again write r equals r0 e to the power minus lambda t, right? And we'll substitute r as r0 by 2. Okay, here we are supposed to find t. Okay, so r0 e minus lambda we have already found out, it's 1 by 5. So t by 5. Okay, so what is the time when the activity reduces to r0 by 2? R0 gets cancelled. What can we do? Actually we can cross it. Okay, so this will become e to the power. Okay, now take log t by 5 will give you log to the base e2, and t will be simply 5 into, so 5 into log to the base e2. Okay, so option D 5 into log to the base e2. Okay, so that is the correct choice over here. Okay, so simple use of your equation of activity for 2 times, for first to find lambda from this data and second to find t from this data. Okay, so let's move to the next question now. So question 13 over here. In this question you are given that the half-life for a radioactive reaction is 20 minutes. T1 is the time the parent atom takes to disintegrate 30% of its initial number, and T2 is the time it takes to disintegrate 67% of its initial number. Okay, you are supposed to approximately find what is T2 minus T1, this interval over here. Okay, Now you can do it the hard way. You can find lambda from here. Okay, you are given the half-life. You already know the relation between half-life and lambda, so you can find the decay constant from here. Then use the radioactivity equation, n equals n0 e to the power minus lambda t. There you'll find use of this relations. Okay, you can use this relation. This was data that I am giving you. Actually, this was not given in the exam, so there you might have lost. Okay, because here you are supposed to do it the smart way. Okay, this was not given in your BITSAT exam. Okay, so here we need to do it the smart way. And what is the smart way? You can try it using the hard way. You can use this relation and try it the hard way too. Okay, using the equation of radioactivity. Okay, but now for now we'll do it the smart way. Okay, you can see that this concentration, okay, or you can write the remaining one. Okay, basically because here they have given it in terms of disintegrating, right? Here we use the equation n equals n0 e to the power minus lambda t. N is the concentration of undecayed atom, right? The one which is remaining undecayed. Okay, so in this case the remaining undecayed is 67%. Again, it's symmetry. Okay, 67%, and here remaining we have 33%. Okay, so the interesting thing over here is that, so what is the half of 67? It's 66 is 33, 33, so 67 is 33.5. Okay, so it's approximately the half of this. Okay, so within this time interval T2 minus T1, the concentration is falling by half. Basically it's half-life, right? So the concentration initial, suppose it's 100, in this interval it becomes 50, right? It falls by half. So basically the time taken for this will be nothing but T half, right? So basically the concentration that falls over here is half. It falls from 67 to 33, right? So basically it's kind of a half. So since concentration falls by n0 to n0 by 2, it means that half life has passed in that time interval, right? So half life is nothing but 20 minutes. And even if you do it the long way, which you were not supposed to, the answer will be very much close to your 20 seconds. Okay, so yeah, that is it from this question. Let's move to the final two questions for the day. So question 14 and 15 over here, the last two questions where we will end our story today. Okay, so let's come to question 14. So after 2 hours, the amount of remaining undecayed material in an radioactive sample is N0 by 16. Okay, so this is the amount that remains undecayed after 2 hours. Okay, you are supposed to tell what is the half-life for this particular reaction. Okay, now we can do one wise thing over here. Okay, instead of doing it by the formula, we'll also do it by the formula for those who don't get it the manipulative way. Okay, now after n half-lives, I told you that the concentration that remains is n0 by 2 to the power n, right? So this is the concentration that remains undecayed after n half-lives, right? You can compare this and this. So this, if you see, it is n0 by 2 to the power 4, right? 2 to the power 4 is 16. Okay, so if you compare this, you'll get that n is equal to 4. So what does this mean? So 4 half-lives have passed. Okay, when the remaining concentration, the undecayed remaining concentration is n0 by 16, we'll have 4 half-lives will be passed. Okay, so 4 half-lives are completed. And what is the time to complete 4 half-lives? It's 2 hours. Okay, so 2 hours corresponds to 4 half-lives, right? So 1 half-life, basically you have to divide both sides by 4, right? So when you divide 4, here also you divide 4, it's half an hour, right? So half an hour or 30 minutes. So option B, 30 minutes is the correct choice over here. Let's do it by the formula way. Okay, this was a wise way. You just compared this with the number of half-lives. Okay, you found out that the number of half-life passed in this interval is 4. Okay, so for 1 half-life, you just divide it by 4. Okay, now let's do it by the formula way. It says n by n0, okay, will be equal to half T by T. Okay, you remember that capital T stands for half-life and t is the time taken, here 2 hours. Okay, now n by n0, n is the concentration remaining undecayed, which is n0 by 16. So n0 by 16 divided by n0, okay, half, and here we have t, small t is time taken, 2 hours for this reaction, and t is the half-life that we have to find. Okay, now n0 will cancel with n0, you can see that, and we can actually cross this. So 2, we get something like this, and 2 to the power 4. We can write 16 as 2 to the power 4. Okay, so you can compare, the bases are same. So 2 by t will be equal to 4, or t will be equal to 2 by 4, right? 2 by 4, which is half, and this is in hours, so half an hour, right? So this is in hours, so half an hour, which is same 30 minutes. Okay, now please remember this formula, and remember that capital T stands for half-life. Okay, we'll also use in this question this formula, because it's used in age of sample, right? This question asks you for age of sample. You are given that you basically have a sample of uranium. Okay, it decays into your lead when the ratio between them, okay, between the uranium and the decayed lead is 3 is to 1. Basically, you are supposed to tell what is the age of the sample. Okay, now we'll use the same formula. N by n0 is equal to half T by T. Okay, here T is the half-life. Half-life is given. Capital T is the half-life. Half-life is given. Okay, and we are supposed to find age of the sample. Age of the sample will be nothing but the time taken for this ratio to become 3 is to 1, right? Now the problem is we don't know n over here. Okay, we can actually guess it. It's very easy. It's n0, right? Let's assume that the initial concentration, it begins only with uranium, right, and then it decays to lead. Okay, so the initial is n0, and after time t, which is the age of the sample, it becomes 3n by 0. What I'm doing is I'm actually making the ratio 3 is to 1. Okay, so what I did, I basically, we want the ratio 3 is to 1, right? So we'll keep the amount of your uh, uranium as 3n0 by 4. I'm dividing it by 4 because I'm adding these two numbers. Okay, and dividing it by 4. Here also I'll divide it by 4, and here I'm making the ratio 3 is to 1. I want 3 is to 1, so I'll multiply here 3. Okay, so when you take the ratio, it becomes 3 is to 1, and when you add it, it becomes n0. Okay, so basically you have to divide by the sum and then make the ratio 3 is to 1. That is what I did. Okay, so the amount of uranium remaining is 3n0 by 4, right? After time t, the amount of uranium is 3n0 by 4. That is the amount that is remaining undecayed. Okay, this has already decayed into lead. Okay, and here you'll have n0. Now just solve this. Half-life, I'll substitute it later. n0 cancels, and what can we do next? We can actually write it this way. Okay, I'll just cross it, 4 by 3. Okay, and we can take log. Okay, log on both the sides, and log, here you'll get t by t, and here you'll get log 2, and here you'll get log 4 by 3, which is 1.33. Okay, here actually you were given the value of log 1.33 and log 2, and so you can substitute here capital T. So basically, if you see, the answer will be, you're supposed to find small t, right? So it will be capital T into log 1.33, okay, again divided by log 2, right? So this will be around 0 point something something, and this is 4.5 into, actually it's 4.5 into 10 to the power 9. Let me check that. 4.5 into 10 to the power 9, yes, and this will be around 1 only, something close to 1 or 0 point something something. So the answer will be in 10 to the power 9. Okay, actually you were given these values, you are supposed to substitute them, substitute this and get your answer. Okay, capital T stands for half-life. Okay, I hope that was understandable. It was easy. Okay, easy enough to get around this question. Okay, so that is all from today's class. I'll give you your homework question and then it's time to say bye. So question 16 over here, this is your homework question. You can pause the video over here, take a screenshot or make a note of it. Okay. So you can give it a try and do let me know the answers in the comment section. The correct answer, of course, will receive a heart from me. And that is all from today's class. I hope you enjoyed it. If you did enjoy it, smash that like button. I'll see you soon in the next video. Till then, keep enjoying physics.